Welcome, gentlemen, and Rob, I'll now turn it over to you to begin today's presentation.
Hi, everyone, and thanks for joining. Again, my name is Rob Reeder. I'm a System Application Engineer at Analog Devices, working in the Aerospace and Defense Group, which focuses on military and aerospace applications. Jerry also joins me from the business side of this group and also has a vast amount of experience in these types of architectures. Both Jerry and I are going to talk a little bit about the value of many of our components, which they bring to several of the applications we're going to discuss today. So let's get started. For the agenda, Jerry is first going to start out covering an overview of electronic countermeasures. He will then move on to RF tuners and talk a little bit about analog down converters, going over an implementation example here. Then Jerry will continue to discuss ADI's power amplifier offerings as well as different technologies that are offered here. From there, I'll chime in discussing how we digitize the spectrum, showing a couple of converter examples that have been developed as well as the many tools that are available from Analog Devices to help in your next design. We have a lot to cover here, so let's get started. Jerry, over to you.
Okay, thank you, Rob. So as an overview of EW-type systems, there are three basic system types. One is electronic warfare support, another is electronic attack, and the third, which we're not really going to cover, is electronic protection, normally ECCM. That's what it's known for in the past. So these systems can get very complex. They range from surveillance through jamming. These systems normally will work together, passing information back and forth, but that's not always the case. And one characteristic that's unique is that you usually have a very limited knowledge of the signals you're going to be receiving. It's things that are out in the world and you're just looking for them, which is different from radar or communication systems, which have similar types of problems, but you do that without the knowledge, do it with the knowledge of the signals you're receiving. So let me just go on from there. So SIGINT systems is one class of systems. Normally, these are slow scanning, narrowband, and a lot of times they're cued by other parts of the system so they know where to go and look. So, that's one class of system. Again, they all have the characteristic that you want to go from antenna to bits. So it's just the pathway through that varies and the requirements vary. So ELINT and COMINT they're a subset of SIGINT, but they have tougher requirements. They may be looking at broader bandwidths, higher instantaneous bandwidths, frequency hopping, things that would really drive the DSP and the A to D portion of the system, not so much the RF portion. So this aerospace and defense spectrum usage is shown here just as an idea of, the range of frequencies that you need to cover. So we have RF components that allow us to do converters and other types of functions over the entire spectrum, and we feed those into the analog components or the analog parts of the system. So it's a pretty broad capability, and the functions that we have available give us a lot of flexibility to address problems, and those problems can vary widely, so we really need all these things. So the technologies that we use to improve SWaP, size, weight, and power, for example, are available to us. We start with the basic process technology, which are the, short, I'm going to say gates because I've always migrated, but the 65 nanometer CMOS lets you do a lot of functions, lets you do RF functions. It enables integration of analog and digital on the same chip. That's silicon integration. The wideband RF devices reduces component count. It lets us cover the widebands. Typically, we're doing 2 to 18 or 0.5 to 18 gigahertz, sometimes up to 40 gigahertz. So devices that we have facilitate that. DSP, it can be used to reduce the requirements of the analog circuits. On the same token, having good analog circuits can reduce the pressure on DSP. They kind of work hand in hand, and we take advantage of both ends of that. And we use novel architectures to solve problems. We don't just try and do things the same way. We look at the total problem and use our intelligence to come up with good solutions. Intelligence and experience. So we have a range of ways that we help with these problems. We start with high-performance building blocks, which, we use and our customers can use to address the problems. We provide support for how to use some of these components because especially the digital parts can get very complex and tricky to understand how to use. So, we build example prototype platforms, or we'll help with the designs to get the best solution. And then finally, we do integrated modules and subsystems. That's the part that's in my group. So we'll take customers' actual operational requirements, come up with architectures and solutions, and build the entire RF subsystem. So getting down to basics, for the basic surveillance architecture is a simple thing in this block diagram. It starts with an RF tuner, which is shown as a simple thing here, but as you see, if you get into it, that can be an extremely complex device that, depends on the environment that you're working in, the types of signals you're trying to receive, etc. That feeds into A to D, into a digital processor. Again, those are also can get very complex, but the basic function is the same. This is the flow. So there are different things that you can do to get improved performance. Or, we can start with the basic simple thing that we just showed. If you want higher sampling rates or effectively higher sampling rates, you can do interleaving by putting multiple A to Ds with a signal RF tuner. Or you can use multiple RF tuners to give you a broader instantaneous bandwidth that has a lot of flexibility. It doesn't always have to be contiguous, so that's a system advantage. These are just a few of the things that you can do. So, may seem obvious, but, what is an instantaneous bandwidth? Well, that's the frequency band that you can look at one time and have 100% certainty that you're going to see any signal there. That's an important thing for a lot of systems. So as you tune across the band, you need to do that quickly because that's going to affect your probability of intercept. Remember, you don't know what's out there. So if you're not looking at the right time, you could miss an important signal. To do things to improve that performance, you can do, as I mentioned before, multiple channels, which will allow you to cover effectively 4 times the instantaneous bandwidth. And also, since you have individual tuners, you could have blocks that are non-contiguous. If you know a general area where the signals will be, you can focus in on those. As you see, a little bit of activity here. And you can also do a broader bandwidth, broader instantaneous bandwidth. This depends on the A to D performance primarily, but it also puts some constraints on the RF portion. So the whole thing has to be considered at one time. You have to look at the whole thing. So you covered the whole band in 3 steps. So these are some examples of some subsystems, so you have an idea what I mean when I'm saying subsystems that we do here. So we do extremely high-performance frequency synthesizers for naval applications, for space applications. They're both direct and VCO-based. The direct are typically ultra-high performance for radar systems. where we have phase memory and very fast switching and state-of-the-art phase noise. To complement those, we have wideband power amplifiers. We're heavily into doing TWT replacements for radars and EW systems based on GaN. And we do RF frequency converters that cover the entire spectrum, because you always have to get the frequency range that you want down into the A to D, regardless of what it is. And it's usually a wider band than you can do in the A to D, so you need converters to bring things down. So some examples of tuners. So again, the challenges in broadband tuners are increased spectral density, unintentional and intentional blockers. You're trying to reduce swap, and you're trying to increase sensitivity. The increased spectral density drives you to needing a higher dynamic range, because you can have a lot of signals and you don't want spurs to come up and confuse the circuitry down later on. It's very difficult once you've created the spur to go back and identify it. Can be done, but it really slows things down, and it puts a big demand on the processing. So we have a scheme that minimizes spurs that we use, which involves upconverting your frequencies into a millimeter wave band. All frequencies are converted, tuned up to that band, and then filtered, and then down converted into the band of the A to D. There's a lot of advantages to this, particularly in terms of image rejection. If you didn't do this, you would need an image reject filter for every block that you do, which can make the assembly pretty complex and expensive and heavy. When we do this, we only need one filter to do the image filtering. Significantly reduces the size and the cost. We have devices that can do this. Going up to millimeter waves, this technique has been known for a long time, by the way, but going up to millimeter waves was cost prohibitive in the past, except for, very high value systems. We get flexible frequency planning, and this gives the lowest spurious performance, because by doing this, we move the really top spurs, which are spurs that are based on multiples of the LO, out of band, so we don't have to filter them. Just a simple spur analysis example of this. If we have a normal, power to the first mixer, which is where most of the spurs are created, we can get greater than minus 55 dBc spurious from something that's a very simple circuit. We don't have to do any additional filtering to get that. And again, that's reasonable, very useful performance from this. So the advantages I'm calling this the minimum filtering technology. The advantage is that we have a signal bandpass filter that does all the image filtering. All the R by NL spurs are above band, so again, you can get excellent performance with almost no filtering. Getting rid of the bulky bandpass filters gives you drastic reductions in size and weight. Without this, you may need a 12 filter switch filter bank, all the filters being tough. So that's a big deal to be able to get rid of them. Again, this architecture is applicable to multi-channel or interleave receiver schemes, as we previously discussed. And you can get higher performance out of this by putting simple pre-selectors in front of this tuner. Again, that's a trade-off that you make when you're looking at your system operational requirements. If you need it, you can do it. The filtering is easier because we don't have the LO spurs, which tend to be very strong and not dependent on the RF level. With the way this is, the filtering is, if you do use filtering, it gets much easier because the spurs are a function of RF level also. So if you move the RF level down with a filter, it goes down 2 or 3 times as much because of the the way the spurs are created. This is an example of what I just talked about, using existing ADI parts. This is something that's, that's real. It'll work, and it takes advantage of the ADI broadband synthesizers, which are very simple chips that will allow you to tune the entire 2 to 18 band with this with 2 chips. So there's not much to say about this except that these are all real parts. You could go and build this thing, and you get a expected performance that's very reasonable. I set this up for 20 dB gain. We end up with a noise figure in the 7 to 8 dB range, and output IP3 as a reasonable number. There are ways to improve that stuff, but as a basic building block, this is an excellent place to start. There are things to do to get higher output IP3. There are things to do to get better noise figure or lower spurs by adding complexity to it. But as a basic building block, this is would be useful for a lot of applications. So just to summarize the converters, so you can get excellent block conversion performance to complement the ADI high-performance ADCs using very simple techniques. You should give consideration to the actual system environment and system needs so that you don't overdo it. You want to get the best compromise between cost, complexity, and performance, keeping in mind that there are some things that you have to do or the system isn't going to work. But most of the time you can find a way around that if you think about it. Many parameters associated with broadband converters, such as tuning speed, step size, phase coherence, phase noise, etc., are all a function of the synthesizer architecture, and they're beyond the scope of this paper. So just let us know to talk about your specific system requirements, because we have solutions for most operational requirements. It's a tough trade-off space between the LO complexity that is required and the system performance needs, so you have to be really careful that you don't overspecify it and drive the cost up. What we've shown is the simplest synthesizer implementation, which could be appropriate for most surveillance missions if you don't require high-speed tuning. Again, we can provide many other synthesizer solutions that will work with this basic architecture. So you start with this architecture, and then you work on the synthesizer to meet your other needs. Typically, tuning speed is the one that drives you the most, because the PLO-based synthesizers are, in the 10s, 20s microseconds response time, even hundreds sometimes. And with direct RF synthesis, you can get tuning speeds down in the 100 nanoseconds range. Also, you can do upconversion with this technique just by reversing the flow of the signals. You have to make a couple other minor changes, but basically you can use the same thing for upconversion and downconversion using the same LO, which is good for repeaters, for example, or anytime you want to send back the same frequency signal that you received. So as I mentioned before, we have a good array of power amplifiers. So if we do the upconversion, I didn't talk about how to do that, but when you do the upconversion, you're going to want to transmit power. We want to go to the antenna, bits to antenna. So we have a family of power amplifiers that cover various power ranges, because not everything needs the same output power, and a wide frequency range. We have a family of devices that we use for high power for radar and EW bands, particularly for TWT replacements. Right now we go up to 8 kilowatts solid-state power amplifiers in X band, and we're working on higher versions to replace TWTs and radars. Compact, efficient. You don't have to replace them. There are a lot of advantages to this, so it's a big deal for us. And again, we're very heavily into that right now. We have similar things for EW type applications. We have 100-watt amplifiers that cover 6 to 18 and 2 to 18. Again, they would complement the down converter. And give you a full system solution. So that's the end of my presentation, and I'll turn this back over to Rob.
Thanks, Jerry. Right now we're going to talk about digitizing the spectrum. As we move deeper into the signal chain, we eventually need to digitize the spectral content under surveillance for the application. Here in this slide, we are showing that in order to scrutinize the signal content in the signal chain, one must be able to capable of wideband sampling. We also need to point out that the system needs to be agile in terms of being able to incorporate fast tuning, or what we consider narrowing the spectrum. So it is critical that the enabler in the system is to use a wideband converter sampling in the gigasample per second range. Analog Devices has a lot to offer here in terms of wideband converter options. In this slide, we're showing a roadmap of our analog to digital converters that have sampling rates up to 2.6 gigasamples per second. Here, the chart displays the noise spectral density versus sample rate, with each converter noted in terms of SFDR performance, or spurious-free dynamic range. Some of the most notable and recently released converters from this portfolio are the AD9625, the AD9680, and the AD6676, all of which I'll cover in more detail shortly. Moving on to the DAC side, there are a handful of offerings here as well. However, I want to highlight the AD9129 in terms of its NSD, noise spectral density, sampling rate, and SFDR performance. Again, I will go into more detail in this DAC a little bit later in the presentation. First, I want to describe the 9625, which is currently our flagship converter in terms of performance and speed. One of the benefits in this device, other than that it's an enabler of high sampling rates and wider Nyquist bands and good dynamic range, it also has the inclusion of some digital post-processing, or DDCs. In the case of the 9625, the DDCs can be used to reduce the data rate to 155 megasamples per second, which ideally helps out the FPGA in terms of reducing the overhead needed inside the FPGA. This simplifies the logic and reduces the burden on the FPGA and possibly reduces the power in the post-processor. So as you can see, today's gigasample per second converters not only pull in from the RF side of the signal chain by offering a wider Nyquist band, but it also pulls in from the digital side as well. This further reduces the complexity of the overall signal chain from both ends by performing the post-processing before the data enters the FPGA. Now let's look at an optimization example using the 9625, which yields the best results given for a front-end design. Here, the input impedance, the AC performance, the signal drive strength and bandwidth, and its passband flatness were measured to yield the best performance for this particular application. Keep in mind that it's important that each parameter have a particular weight of importance per the application when optimizing. In some cases, for this example, bandwidth, which might be the most important spec, and therefore other parameters are allowed to suffer a bit just to get the bandwidth that's achieved. Here in this example, the input network for the 9625 converter is shown. Each resistor in the network can be treated like a variable. Essentially, the impedance matching network is roughly the same, but the yielded results between the three examples are different across the measured parameters as shown in the table. So in summary, as you can see, that case 2 would be more desirable for two reasons. One reason is because the passband flatness only has 2 dB of ripple across the 2 gigahertz region, and 2, the input drive is 3 dBm less than in case 1. This puts less of a constraint on the RF gain further up the signal chain in order to achieve full scale of the high-speed converter. Therefore, in this example, case 2 seems to be the best match. So here we have this solution available today. The part number is the AD-FMC ADC2-EBZ. This is well suited for multi-board synchronization and supports phased array applications. It also has an onboard power supply and sampling clock oscillator. The customer only needs to provide the proper analog input IF for their application for the evaluation. Another example of a gigasample per second converter that's available today is the 9680. It's a 14-bit, 1.25 gigasample per second dual ADC that has integrated EDCs per channel and again uses a JSD 204B output format digital interface. This part in wideband mode yields a typical performance of 67 dBFS SNR and 85 dBc SFDR at 1 gigahertz IF. It also has a sample bandwidth of 2 gigahertz. This comes in a 64 LFCSP package and is also sampling and evaluation boards are available today. Other variants are also available, such as the 9234, which allows for slightly lower 12-bit performance if needed for your application. If we look on the right-hand side, you'll see here one of our active driver offerings called the ADA 4961. This is a low-distortion DGA, that's a digital gain amplifier, that has a 2.5 gigahertz bandwidth, and that was specifically designed for AC-coupled wideband applications and driving gigasample per second converters. One of its features includes a fast attack, which makes it a good choice for radio receiver architectures where the received signal may be varying in strength and the possibility of jammers or blockers exist. The fast attack feature can be implemented with the overload sense feature of the converter in order to implement a fast back off when the converter is in the overranged condition. Looking at one particular application, this shows the ADA 4961 amplifier driving the 9680. Here, this match provides the best performance results as the drive is well suited for interfacing with a 50 ohm output load, providing good bandwidth response. This solution is also available, shown here, called the AD-FMC ADC4-EBZ. This board has 4 channels of the ADA 4961 amplifier and 2 dual 9680 converters. Again, there is an onboard power supply and a sampling clock circuit using the 9528. This is not shown, it's found on the back side of the board, but it's used to clock and synchronize all of the channels, all the converter channels on this board. Each channel can also be independently gain controlled from the supporting amplifier stage throughout the ADA 4961. Another recently released converter, the AD6676, is a highly integrated IF subsystem that can digitize RF bands up to 160 megahertz in width, centered on an intermediate frequency, or IF, of 70 megahertz to 450 megahertz. Unlike traditional Nyquist IF sampling ADCs, the AD6676 relies on tunable bandpass sigma delta ADC with a high oversampling ratio to eliminate the need for specific IF SAW filters and gain stages. This results in a significant simplification of wideband radio receiver architecture. Integrated on-chip DDCs and decimation filters reduce the complex data rate in order to manage it between 62 and 266 megasamples per second. This provides a 16-bit complex data output that is transferred to the host via single or dual lane JESD 204B interface, which supports line rates up to 5.333 gigabits per second. Leading our DAC portfolio, the AD9119 and the AD9129 is a high-performance 11 or 14-bit RF DAC that supports data rates up to 2.8 gigasamples per second. The DAC core is based on a quad-switch architecture that enables dual-edge clocking operations, effectively increasing the DAC's update rate to 5.7 gigasamples per second when configured for mixed mode or 2x interpolation. This offers offers high dynamic range and wide bandwidth up to 4.2 gigahertz. The AD9129 also includes several features that may further simplify system integration. Those of which include a dual-port, source-synchronous LVDS interface that simplifies the data interface to the host FPGA or ASIC, and a differential parity bit monitor that looks at the integrity of this interface. Also, the on-chip delay lock loops, or DLLs, are used to optimize the timing between the different clocking domains. Lastly, it's worth mentioning ADI's tools, which are the glue that integrate our technologies into your design. ADI is constantly innovating to bring support to our customers to help them get their differentiated system solutions to markets faster. Especially relevant are on the ADEF focus site, which contain signal chains, recommended components, links to appropriate articles, and application notes. So please check out www.analog.com/ADEF, ADEF, in order to help you with your next design. Again, thank you for watching, and for more information, please visit these two sites listed here for additional content and product offerings. Thank you.
All right, thank you, Rob. We're now going to get started with our first question. It looks like our first question is a throw out to either one of you. In many of the next generation ADCs, I can see that optional digital down converters are available. Can you provide some insight as to the benefits of using these?
So I guess I could take that from the point of view of the RF tuner. Having that function in the chips allows the center frequency that you're looking at to be moved, so you can zero in on a particular area of the wideband spectrum that came in. That makes life easier for the tuner, since the tuner can then just act as a straight block converter, and it simplifies the RF architecture. It's a case of the two things working together to get the best performance, and that's an important feature that's very beneficial.
All right, fantastic. We're going to move on to our second question here. Are there any other future developments in the works for higher sample rate ADCs greater than 2.5 GSPS, say like 4 GSPS or higher?
Yeah, I'll take that one. Yeah, at Analog Devices, we're embracing the future for wideband RF ADCs, and the trend right now is for higher sampling converters with wider Nyquist zones. So certainly there is a future that's going on here. So I'm sure we'll continue to develop these types of products as the industry demands it.
All right, thank you, Rob, and thank you, Jerry, for the previous one. What are some good recommended frequency references for the PLL based on based clocking products?
I'll grab this one. There are many different choices of references that are out there, obviously. Typically, what we use is Crystech, Vectron, Bell Pay Fisher, Epson, Titan, and RFMD for a lot of our evaluation platforms.
All right, thank you, Rob. Next question for you. In the analysis for the 2 to 18 gigahertz frequency conversion, you recommended an up and down approach. The system I'm developing requires coverage to 40 gigahertz. Would this be handled in the same way?
Normally, you wouldn't do that. What people usually do is block down convert the 18 to 40 gigahertz range down into the band that the tuner is working. That is much easier than trying to completely step across that whole band. It's you take advantage of the existing tuner by just putting a fairly simple block converter to knock, say 18 to 27 or 27 to 40 down into the 2 to 18 range. That's the approach that people have been taking for years, and that's the one we would recommend. We have components that allow that. It's mainly a function of the mixers, and we already have the synthesizers, simple versions of the synthesizers that we talked about before to do that conversion.
All right, thank you, Jerry. The next question for you. It looks like we have time for just this last one. What if the bandwidth for my application is narrow, say only 100 megahertz band, but is located up at 2 gigahertz or more? Do the same details apply? In other words, do I still need a GSPS converter?
Well, keep in mind that even though in this presentation we covered gigasample per second converters, not all applications require one. Many radar and other instrumentation applications use converters in the hundreds of megasamples per second to capture higher IF, with the addition of more down stages in the signal chain.
All right, thank you, Rob. On behalf of our guests, Jerry Cornwell and Rob Reeder, I'm Chris Keach. We'd like to thank you for your time, and we hope you have a great day.